Okay, section 5.3, we have definite integrals and antiderivatives. Definite integrals, and a definite integral is an integral that we actually can compute the value. Later on we'll have some that are not so, that are just formulas, but a definite integral is when we actually plug in those values. The other thing, antiderivatives, and we already talked a little bit about how those are related. Antiderivatives. Definite integrals and antiderivatives. Okay, so first thing I want to note is that on page 285 there's an awesome table. Page 285, there's an awesome table. I don't know why I mixed up my capitalization there, but there's an awesome table there. It has a lot of just facts in general about derivatives. I'm sorry, about integrals. And I was going to say it's very similar to the derivatives. Like a multiple of an integral is the same as the integral of the multiple. You know, the constants can go in and out and whatnot. So just look that over. A lot of those things should be intuitive to you based on what we know about derivatives. But I wanted to note that there, and I'm going to use that later when I do a couple problems from there. Okay, one thing I want to note here, average value. Okay, if we have an average value, well, that's kind of like the mean, and we've done that, you've been doing that for years, the mean. Well, what is the mean? The mean is you add everything up, and you divide it by the number of things that you added. So you add up, and you divide by the number of things. Okay, when it comes to our ideas about integrals, we add up all those rectangles and then you divide by the number of rectangles. Or another way to think about this now, when it comes to an integral, this is going to be like the area over the width. Okay, so let me draw a little picture to hopefully maybe convince you of this. Okay, there's our thing. I want to find the average value of this function. Okay, so it's like I want to find the height of the function. Well, to find the height, think of this like a bunch of rectangles. You take the area divided by the width, that'll give you the height. Okay, so if area is width times height. If I take the area divided by the width, that'll give me the average height. That'll give me the average value of that function. And then they have the calculus way of writing this out. The area is the integral. The integral from a to b of some function. Don't forget to put the dx at the end. Over the width. Well, that's the difference of b and a. Over b minus a. And in the book, the formula they write the b minus a over to the side, 1 over it. I like to have it like this. It's a little more compact. So this is the area over the width. And that'll give you the average value of a function between b and a. And you can choose those, and it will give you different values for different values of b and a. One more thing I want to note here in my notes. Okay, the integral as the antiderivative. The integral as the antiderivative. Okay, the integral is the antiderivative, and let me first I'm going to give you the formula. I just like to go right to it. Don't make you wait for it. So the integral from a to b of f of x, this should be a lowercase f, of f of x is equal to capital F of b minus capital F at a. Okay, and this gives us, well, what is capital F? Well, let me see. Let me say f of x is the derivative of capital F of x. So this is the antiderivative. This is the opposite of the derivative of this. So I have to find some function in which the derivative will give me the function that I started with. Okay, so you just have to work backwards, and and that will give you the integral. That'll give us a nice little way. We don't need to use triangles or all the different shapes we've been using. This will work on any function that we can find the antiderivative of. For polynomial functions, we just use the opposite of the power rule, and that will take care of all those and some of the other facts we've known as well. So that's actually incredibly powerful. So that is the integral is the antiderivative.